Right, so welcome everyone, and thank you for joining us. So today, for the start of the new semester, it's our great pleasure to have Sylvain Carrozza, who will tell us about edge modes as dynamical reference frames.
Okay, thanks, Mark. First, thanks a lot for inviting me. It's a pleasure. I hope you can get something out of this work. We are relatively new to this edge modes business, but I hope we're bringing a new twist to it, hopefully. And what I'm gonna tell you about is work together mainly with Philippe Heun. So there's one paper out already, and at the end of the talk, I will also mention work in progress, which is more directly related to gravity, together with Philippe again and Stefan Eckels. And both of them are online, so maybe, so that you know. And so, let me start with kind of general motivations where to tell you a bit how we got interested in this edge modes business, which is maybe a slightly different perspective from what you guys are doing. So with Philippe, we started thinking about space-time regions with the topology of a cylinder like this, and we were wondering how to treat them as a thermodynamical systems, possibly out of equilibrium, and how we could write down general fluctuation relations for how these subsystems interact with their environments through a kind of work influx or something like this. And the hope, the reason for doing so is, well, of course, like trying to understand better in which sense quantum gravity might be a theory of the thermodynamics of space-time in some sense. And also the hope was that if we can treat, you know, this boundary in gravity, this time-like boundary as a dynamical object, even though classical, that may serve as a good Heisenberg cut in the quantum theory, and one which is compatible with the background independent nature of gravity classically. Okay, but so that's the kind of general motivation. But in exploring these ideas, we had to understand, in fact, the role of edge modes in gravitational systems and more generally in gauge systems. And so we started thinking about that as well and trying to get an understanding from a kind of more physical understanding from this point of view. And so let me start with a kind of cartoon picture of why these edge modes are necessary in gauge and gravitational theories in bounded regions. So imagine here on the right panel that you have here I have represented, sorry, a Cauchy slice that is going through the region M here. So sigma is what lies inside the region M, and sigma bar is what's outside. Sorry. In gauge theories, because we can have non-local observables, gauge invariant non-local observables like Wilson loops that may have support both on sigma and on its on sigma bar. In order to account for these observables, one may need to to split these observables in two, and in order to make them gauge invariant, people have proposed that one should introduce edge degrees of freedom here that have a specific transformation properties under gauge transformations, and that can be used then to address in a gauge invariant manner these half Wilson loops, if you wish. And so that's what I will be focusing on in this talk. And of course, there have been a lot of work in this direction. So here I've just cited a few of the main characters here, but this is a huge literature, so I'm not even trying to be exhaustive. But okay, and let me try, before I dive into the details of our construction, let me try to contrast it, with what has been done before. So I would say that the original edge mode constructions, as was pioneered, for example, by William Donnelly and Laurent Fredel, is of a kinematical nature, in the sense that one focuses on one partial Cauchy slice or even a causal diamond, and one is allowed to vary the Cauchy slice inside the causal diamond, but keeping the corner fixed, so the boundary of the partial Cauchy slice fixed. And it's really a construction that is inward. So you start from the Cauchy slice and you extend the phase space associated to the Cauchy slice. And in doing so, you need to, at some point, postulate the existence of these edge modes. So because of that, the physical interpretation is maybe not entirely transparent. But once you postulate them, there's a nice way of obtaining their symplectic structure by requiring some kind of extended gauge invariance condition that I will come to later. And this is nice because, well, this minimal setup leads you to a universal corner symmetry algebra that has been used a lot in this recent developments, going under the umbrella name of local holography. Okay. And now the kind of approach we try to follow with Philip is more dynamical, in the sense that we focus instead on bounded regions which have a time-like boundary. And it's also kind of the reverse process of this phase space extension, because we instead start from the global phase space for region M and its complement M bar. And we derive the edge mode structures from this global phase space. So we don't need to postulate them; they are already there in the global phase space, and they arise because we construct a dynamical reference frame in this global phase space. And from there, from there, we have also a constructive way of deriving the symplectic structure associated to these edge modes. But it's slightly different from this one. Instead, we use a kind of dynamical input. So we use some conservation equation for the symplectic structure that defines uniquely the boundary term. Anyway. And what's and this is I believe this derivation is a bit complementary to this one, to the kinematical one, because well, the boundary symmetries that one gets are slightly larger, because they allow you to move along the time-like boundary, not only so you don't have to keep the corner fixed, and also it's possible to analyze the interplay with the boundary conditions along this time-like boundary. Okay, so that's the kind of setup, and now I will try to explain this in more detail. Okay, so this is the outline. The first 4 bullet points here will be mainly about gauge theory. So I will focus on simple examples. So that's about the paper that is already out. And the last part that I hope I get to will be about gravitational edge modes, and will be more about work in progress, so unfinished business. Okay, so let me start with kind of defining some notations and some standard background material on the covariant phase space, so that we are all on the same page, even though for most of you this will be pretty much standard. So I will start from I will use the covariant phase space. So I will assume that the dynamics of the field theory of interest is defined by a Lagrangian density, which is a D-form on spacetime, and the fundamental dynamical equation is this variational equation. So when you vary this D-form and you express that variation in terms of the fundamental fields, phi A here in some coordinates, you get a first term that has to vanish and gives you the equations of motions, EA. And because of in doing so, one needs to perform some integration by part. One obtains a boundary term that here g theta that encodes the symplectic structure, and this theta is called the symplectic potential. So let's look at a simple example for Maxwell. The field strength dA enters the Lagrangian in this way, and when one takes the variation after doing some integration by parts, one gets a first term that contains the bulk equations of motions, d star f equals 0, and the symplectic potential, which is minus delta A wedge star f. Okay. And so the symplectic potential is useful because one can get the symplectic or pre-symplectic current from it by just varying once more, so taking a delta of this theta, and that defines a symplectic current, which has these nice properties. So it's field space closed. So yeah, sorry, I forgot to say in this talk I will do as usual. So I will review this. This variation delta as a field space exterior derivative. So when I say that delta omega equals 0, it means that it's a field space closed. It's anti-symmetric, so it can be used to define a symplectic structure, and it's also a closed-on shell, which can be proven quite easily from this formula, but I won't do it. And this condition here is very useful because when one integrates this current over a full Cauchy slice, so here in the global spacetime, so I integrate over sigma and sigma bar together, I get a symplectic structure, which is a symplectic form, pre-symplectic form, in fact, that is independent on which Cauchy slice I use, provided that I have good fall-off conditions that I will assume.
Sorry,
yeah. Yes.
The notation maybe is a little bit confusing, but the presymplectic form would be associated to the integral over only one of the slices, right? Otherwise, it would be weird. It would be assigning the phase space not to initial conditions, but to initial conditions and final conditions simultaneously doesn't look good to me.
No. I mean, so here's the drawing. Sigma and sigma bar, they are like so this the
okay, thank you. I see.
Complementary.
Yeah, sure. Okay. It's not sigma, it's sigma prime. Very good.
No. Sorry. Yeah.
Thank you.
Thanks for the question. All right, and then still further background. So just to fix notations and to explain, remind ourselves how this connects to the standard Hamiltonian formalism. So on top of the space-time exterior algebra, as I said, so which I will denote in this way. So there's the exterior derivative D, the interior product here, and the wedge product. There's a field space exterior algebra, which is given by this delta. Then field space interior product that I will denote by a dot, and the wedge product that I will keep implicit. And these things are compatible in a nice way. So for example, D and delta, they commute, and both they square to 0. But okay, I don't want to spend too much time on this. And so one can define a field space vector fields from the point of view of this exterior algebra here. So formally, you could write it like this, as a kind of linear superposition of function derivatives. But equivalently, you can define a field space vector field by its contractions with the basis of one forms. So, for example, in this way. Okay, and then in the covariant phase space formalism, the vector fields we are most interested in are the ones that are Hamiltonian or integrable, which means that they are vector fields that are, when contracted with the symplectic form, give a field space exact term. And the Q entering this formula is called the charge usually. And finally, just to remind ourselves of how this fits with the standard Poisson bracket formalism, the Poisson bracket is obtained from the symplectic form just by contracting the corresponding Hamiltonian vector fields with the form, and one obtains the brackets of the functions that define the vector fields. Okay, that's it. And finally, just further a bit more background. Sorry for this. So we will need to discuss gauge symmetries. So in this kind of abstract formalism, gauge symmetries, just to remind ourselves, They are field space vector fields, okay, here that are null directions of the symplectic form on shell, at least. And so, for example, in Maxwell, one example of such a vector field is a generator of a gauge transformation like this on the connection, which you can define in this way in the covariant phase space language. And these vector fields, they generate a gauge group. So and because they are null direction, that means the presymplectic structure is not invertible, so it's not a symplectic structure. In order to obtain a phase space, a physical phase space, one needs to quotient the space of solutions by the gauge group, and in doing so, one obtains a symplectic structure now, omega hat, on the space of gauge orbits. Okay. So that's all for the kind of summary of the covariant phase space formalism. And now, just to tell you what I want to do from there. So I've told you about. I've reminded you about this arrow here, how to go from the space of solutions to a phase space. And what I will be interested in is this type of arrow here. I want to go from the solution space in the full global space-time to a solution space for subregion M, which has this topology here. And I want to find a kind of an automatic procedure to derive such symplectic structures from the global one. And so the type of questions we'll be asking are what type of gauge invariant boundary conditions we need to impose on this time-like boundary gamma that allow to view this subregion M as a closed subsystem. And once we have such boundary conditions, how to derive a presymplectic structure for this subregion M from that of the global spacetime. And one last point, we will even be able, in fact, even though I will not spend too much time on that part, it's also possible to move this construction off shell and to derive, in fact, variational principles for the subregion M that also impose boundary conditions from the global space of from the global variation principle. Okay, so these are the questions, if there are questions at this point, because then I will try to answer them. But, all right, so one last piece of background material I would like to give you is roughly how this original Donnelly-Fredel edge mode construction works. And so the key point I want to emphasize is that, so remember, this is about focusing on a causal diamond or even a single partial Cauchy slice. And the main postulate that they use in this paper is the invariance of the presymplectic structure they want to construct under field-dependent gauge transformations. And that's the part I want to emphasize, is that it works only if you look at field-dependent gauge transformations. So it's a bit abstract, I would say, without further justification. And but it's quite efficient because it allows you to motivate the introduction of edge fields contributing to the presymplectic structure, so to have this extended phase space structure. And it works quite generally for gauge theories as well as gravity. And let me illustrate these steps simply in Maxwell theory. So, so remember in Maxwell theory, the symplectic current is just delta A wedge delta star F. And so a naive presymplectic structure we could think of for the partial Cauchy slice, so for the subregion M, is to just integrate this omega on the partial Cauchy slice. But this has a defect. So if you perform a gauge transformation with respect to a gauge parameter alpha that is field dependent, so in the sense that delta alpha doesn't have to vanish, the variation of alpha doesn't have to vanish, one finds using the equations of motions that this on shell does not vanish. You get a boundary piece here. And that's where, in order to correct for this, you need to kind of postulate, introduce by hand, an edge mode field phi that transforms in a specific way under gauge transformations. So, for example, like this. So it's shifted by alpha. And once you do that, it's pretty clear how to correct for this lack of invariance. You just add a boundary piece to the naive presymplectic structure, and this has the effect of canceling the unwanted term on shell. Okay, and so in this way, this kind of abstract postulate leads you to a unique, more or less unique symplectic structure for these postulated edge mode fields. But okay, and so the question from this point of view that I would like to illustrate a bit is that, well, in these steps, it's pretty, what we have done essentially is to promote gauge parameters to dynamical fields. And also we have used this idea of gauge invariance under field-dependent gauge transformations, which is not so obvious why it should be relevant. And so there's a bit the question of what does this all mean? Okay.
And maybe also, how does it compare with Mark's technique, where he does the different slicing or whatever he calls it?
Maybe I'm not so familiar with that.
Well, because of this field dependence, now the generator is not integrable anymore. You cannot say that the nether charge is the generator. And I understood from previous talks by Mark that in this case, they can do some slicing in the phase space that allows them to recover. Is there a relation between these techniques or not at all?
Maybe. I am not, well, Mark.
Mark is there. So
no, I think not at this stage because they kind of fit two different objectives.
But they do get now an integrable charge out of these field-dependent transformations. Isn't that also the goal of your different slicing procedure?
Yes, I agree that you get the same thing at the end, but I think
I'm not sure you get the same thing. You get integrable charges. We don't know if we get the same. Here you get 0 as the integrated charge, right?
Well, but you could argue, as Laura and William did, that you have these other kind of symmetries that give
the
you
right
which
action.
at the end of the day is the same as your kind of addressed charge. So.
And
then the result would be the same as with your method, or it's not clear yet?
I don't know, in fact.
Okay.
It's a good question. Yeah.
Okay. And okay, so in fact, since you were mentioning these other transformations, so another salient point of Donnelly and Fradel, I think, is the fact that once you have this extended presymplectic solution space, so that contains the connection and this edge mode phi, one can define two distinct kinds of transformations relative to this presymplectic structure. The first one are just gauge transformations that act as I defined, so on A in the usual way and on phi in the way that we have postulated. And these are in the kernel of omega m, just as we demonstrated. So they are gauge transformations. And then there are boundary symmetries that are defined in a similar way, but act only on the edge mode field. So they shift the edge mode field here by minus rho, for example, and leave the connection alone. And these boundary symmetries now are integrable on shell, and they are not trivial. So they record some information, for example, about this flux of the field strength star. Okay, and the second point we want to understand from this kind of dynamical perspective is how to interpret these physical these symmetries in the reference frame context, and how do they, what's the interplay of these boundary symmetries with boundary conditions. Okay. All right, that's all for the kind of background material, and now I will try to tell you a bit more what is in the paper. So, but before I do so, I want to start with a very simple time model that captures, I think, the essence of the main construction that we have in this paper for gauge theory. So the example is very simple. It's a system of n particles on a line subject to a translation invariant dynamics. And so, for example, something like this. Because of this translation invariance, you have a gauge symmetry in the system, which is just a global translation of the position of the particles by an arbitrary function of time. And what that means physically is just the fact that the only physical observables are about relative distances, not absolute distances. Okay, so that's a very simple example. And now, when you start cutting this, splitting these systems in two halves, like for example, a region M that contains a number of particles and a region M bar that contains the others, there are different types of symmetries that transformations that will look the same from the point of view of M, but that are completely different from the point of view of the global phase space. So, for example, in the first line, I have pictured a gauge symmetry. So I'm just translating everything by the same function alpha. And so, as I just said, it's like doing nothing. And on the second line, I have something that we will consider as a symmetry that changes the relative distances between the first group of particles and the second one. But from the so I just translate everything in the second particles second group by the same constant and do nothing on the first group. And well, from the point of view of M alone, these two transformations look the same. So one could think that both of them are gauge symmetries, in fact, because they are shifts by constant functions by the same function of time. But obviously, from the point of view of the global phase space, they are not. This one is a physical change of the state of the system, and this one is not. And so, from this very simple example, it's clear that if we want to be able to distinguish these two types of transformations when discussing the dynamics of M, one needs to include an additional reference frame or dynamical system, for example, in the form of this particle R here, into the description of the region M. And if we do so, we will be able, in fact, to distinguish these two types of transformations. And so the kind of claim that we have in this paper is that, well, this simple model is a good example of what's going on, in fact, in gauge theory. So the edge modes a la Laurent and William, they can be understood in the same way as kind of a dynamical reference frames that one constructs in the complementary region of M in order to keep some information about how M relates to its complement. And so yeah, and that's it essentially. So that's the main idea. Questions? Oh, okay. Okay, and then, well, there are many differences between this simple mechanical model and gauge theory, but at least this kind of qualitative aspect is identical, I want to say. Okay, and so this brings me to the introduction of dynamical reference frames into the gauge theory picture. So in fact, this is a philosophy that is underlying many recent efforts in the quantum reference frame literature, where there the idea is to use quantum systems as reference frames instead of classical systems as reference frames. And here, what we are doing is to import this idea in gauge theory and gravity, in the sense that we want to use dynamical systems as reference frames instead of background systems as reference frames. Okay, and the formal definition is quite simple. So given a symmetry group G acting on some system S, a dynamical reference frame is just the following data, a subsystem of this global system S that I denote R for reference, with a certain configuration space, and together with a free group action of the symmetry group on this curly R. So a very simple example is, for example, a clock measuring time could be thought of as a U1 symmetry group. So you have a needle that when being acted on by U1, which is well, how the time of day as it passes, moves the needle by some angle. Okay, and that's a dynamical system that you can use to keep track of evolution in the rest of the system. Okay, and the reason why it's useful is pretty clear, is because it can be used to parameterize G orbits and construct invariant observables without the need to refer to a background structure. So in gravity, that should be useful. And okay, what we are going to do is just to apply this this general definition to the local gauge group of a gauge theory instead of just a global symmetry like you know, time translation. Okay, so let's do it.
Is the role of symmetry so important here? Like, I mean, usually in completely dynamical situations in gravity, you don't have any symmetries. What is the logic? What do you have in mind?
Sorry, I didn't.
Why are you invoking the existence of a symmetry group? Like, are you interested at some point in dynamical gravitational systems, situations in which there are no isometries? What will you fetch in that case as this group?
I'm just saying the local gauge group would be just
like the diffeomorphism group.
Yes.
Ah, okay, okay.
Yeah,
So
it doesn't need to be a global symmetry. You can use this reference frame idea for local symmetries, gauge symmetries, sorry, as well. That's the idea. Okay. And so let's look at a very simple example of a gauge theory now. And suppose it's a pure gauge theory. I just have the gauge connection transforming in the usual way. So this is my notation for gauge transformation. Sorry. And now in this context, we can define quite generally the notion of dynamical reference frame for the local gauge group in a similar way. So the only difference is that now we need to take into account the local spacetime structure. So the definition is that a reference frame for the group here, G, is a functional of the connection and other dynamical fields that transforms in a specific way under gauge transformations. And the transformation is this one. So it says that under gauge transformations, this local reference frame transforms under a free group action by the group locally. So here this dot is assumed to be a free group action of the local gauge group, and so that, yeah, that's just the definition. And one primary example of such a reference frame is one which is valued in the group itself, and where the free group action is just the left multiplication in the group. And so that's the kind of example I will focus on in the rest of the talk, even though this is slightly more general. And so because of that, I will denote it by the letter U instead of R. So U to remind ourselves that it's a group valued quantity. And now this free group action is simply the group multiplication. Okay. Okay, all right. And that's and so the claim is that whenever you can construct such an object in a local gauge theory, you can use that as a reference frame to construct gauge invariant observables from.
Sorry, Sylvain.
Yes.
Can you give a concrete example to guide?
Yes.
A bit better. Like, I mean,
it will come in.
In Maxwell's equation, in Maxwell's case.
Yes, it will come in 2 slides. Is it okay?
Okay.
Or?
Okay.
Yeah. So just for the moment, just I just want to say a few more things. Just assume that we can construct such a functional. So it's kind of non-locally defined, but it gives you a reference frame at every point in space-time. I will tell you how to do it in an example. And the claim is that if we have such a reference frame, we can decompose any other local field functional in the field theory in a canonical way relative to that frame. And the decomposition is as follows. So suppose you have some field, local field phi. You can decompose it as an invariant part plus a gauge part. And the important definition is the definition of the invariant part here. So the definition is as follows. You just take your field phi, you act with the gauge transformation by u minus 1. So this group value reference frame. And you can check that this object in fact is gauge invariant. So it's a kind of frame dressed observable that is gauge invariant and tells you how phi relates to the frame that you have constructed. And then the gauge part is simply the difference between the invariant part and the full field, and it carries the gauge dependence of the field. Sorry. and so this in fact I should say that it's also a kind of a covariant realization of something that has been studied a lot in the canonical context, in the context of relational observables. So a slightly more general definition of this object is you could define this relational observable O of phi and nu evaluated at some configuration G and spacetime point X that is defined in this way. So I have just inserted this G minus 1 here, this group parameter, and this observable is a gauge invariant observable that answers the question of this type. What is the value of phi here when the frame U is in orientation G? Okay. And the reason for that is that, well, when you evaluate U at G, this is just the identity and you get phi. Okay. That's essentially the idea. And these type of observables in the canonical context have been studied a lot by Bianca Dietrich, for example, or Carl Orwelli in the 90s. Okay. And here it's a slightly more simpler to formulate them in the covariant context actually. But okay. And okay, and now let me come to an example as Alejandro was requesting. So a very simple example, but now specifying two edge modes. And so the point is that edge modes arise from this kind of general formalism for constructing local reference frames in gauge theory when applied to local fields on this time-like boundary gamma. And a specific functional of a specific frame functional that has support, let's say, in the complementary region M bar. So that can be used to relate what's going on in M to what's going on, let's say, asymptotically. And so a concrete example is in the simplest possible context of a pure gauge theory. So in this context, in order to be able to define such a frame, you need to assume that there is some kind of asymptotic boundary, gamma naught, where gauge transformations are required to vanish, so that you can use this this asymptotic boundary as a background frame. If you make that assumption, so you could think that, for example, this asymptotic boundary is just a way to encode the fact that you have, I don't know, massive degrees of freedom that allow you well, that you can use as dynamical frames, but they are so massive that they are background, in fact. But okay, let's not get into this. So a simple way to obtain a frame is just to shoot a system of path and compute the holonomies along the system of Wilson lines from a point on the asymptotic boundary to a point on the boundary gamma. And this, so it's a non-local functional of the connection in the complementary region M bar that looks like a local field on the boundary gamma. Okay, and that transforms exactly as we assumed it does, like in this way. You know, that when you perform a gauge transformation, you just act on the left by the gauge transformation. And once you have such a thing, you can just dress any local field you would have near the boundary gamma and decompose it into a gauge invariant part that we call the radiative part in this context, just because it relates to what happens on the boundary, plus the gauge part. Okay. Does this clarify a bit?
Yeah.
Okay. And of course, there are many ways of constructing such frames. If you want to have more local constructions, you need to introduce matter. But here in this context, yeah, to keep things simple, we looked at pure gauge theory. Okay, and now from this point of view, so this kind of a frame, which is non-locally defined in this way, is what will become the edge modes once we restrict to the subregion M. But we can already define the symmetries a la Laurent and Will at the global level. And so, for example, in this example, one could think that there's a one type of operation we can do is to change the background reference frame on this asymptotic boundary gamma naught, and this is implemented by this. Its effect on the frame field is to transform it by a group multiplication, this time on the right, because we act here rather than here, and where this parameter is also a field independent quantity. So these are really the symmetries that will become integrable, that will carry integrable charges, and the interpretation of the symmetries in this construction are simply that they are just changing the state of the system by just changing how the local subregion relates to this dynamical reference frame. Okay, and notice that here it's clear also why these symmetries, they act by multiplication on the right, while the gauge transformations, they act by multiplication on the left. Okay, I don't know. Okay, it's quite late, so I will go a bit fast. Then there's another kind of transformation one may consider, which is a bit similar, but one can ask the question, so what happens if we now change frame? So for example, in this context, we are just using a different system of path and different set of holonomies to construct a frame. Of course, it's possible to map from one such frame to the other, and this takes the form of this looks a bit like a symmetry, except that now this symmetry transformation is field dependent, of course, because these frames, they are field dependent. But the interpretation is of course different, because such a transformation is just a change of description. It doesn't change the physics. What we are doing is just mapping one set of relational observables here related to a frame U1 to another set related to the frame U2, but for the same physics. And if anything, I think this if one would want to, I don't know, connect this postulate that of Laurent and Will, that the symplectic structure should be independent under invariant under field dependent gauge transformations, one could connect it to this type of transformations and say that this is implementing the idea that we want the symplectic structure to be to look the same in any frame. So in any, but this is not the route we are taking. Okay. So that's it for now. So I think just to summarize what I have argued at this stage is how to introduce these dynamical reference frames at the global level, and how they already capture some features of these edge modes. And now what is left to do is to understand how to restrict to the subregion M, but keeping sufficient information about the frame. And so what we want to do is the following. So let's remind ourselves of where we are. We have this subregion M and this time-like boundary. And we want to go from this global space of solutions to a regional one for this subregion. And the way to do so is to, well, foliate the space of solution S, the global one, with respect to some suitable functionals of the fields on the boundary here that we will ask to be gauge invariant. So I foliate with respect to this function X of the gauge invariant fields on this gamma here relative to the frame equal to some background function. Once when we have that, we can restrict to a particular leaf, and this is like taking imposing a boundary condition, a gauge invariant boundary condition that may involve the frame. And finally, we just discard what's going on into M bar, except for the information that we need about the frame. Okay, so that's the strategy. And just to tell you a bit more how we choose this foliation. So what we want is to, because we are in fact imposing boundary conditions with this through this foliation, what we want is to fix sufficient data on gamma so that well, we have a well-defined variational principle, but also not too much. And so the naive guess would be to ask the symplectic current to vanish, so to fix boundary conditions and the Lagrangian submanifold of omega. However, in general, this might fail to be gauge invariant because omega does not contain only gauge invariant degrees of freedom. So in fact, if we do so, in general, we are both imposing a boundary condition and gauge fixing and a gauge fixing. And in order to disentangle the two steps, a better choice is to impose a boundary condition only on the gauge invariant part of the degrees of freedom. So the reference frame dressed degrees of freedom.
But Sylvain, would you agree that if you do this, you don't have a unique solution in the bulk in general? So how do you construct the phase space in this way?
So you construct the presymplectic
because your notion of phase space, you should have one point associated to one solution. But if you don't fix the gauge components on the boundary, you don't have a unique solution.
Yeah,
so how do you...
So our point was not to say that you should not gauge fix, but rather that there is a way to preserve, to construct first the presymplectic space for the subregion where you still have all the same gauge symmetries that you had in a global phase space. And once you've done that, if you want, you can either take a symplectic reduction to get a physical phase space or a gauge fix, but as usual. But the point is that you don't need to do everything at once, and you can keep things slightly clearer with respect to the physical meaning by just imposing boundary conditions that have a direct physical interpretation that don't involve gauge fixing, and then if you want later on, you can still compute the physical phase space.
But I think what Simon is saying, or at least this is what is confusing me as well, is imagine there is no gauge symmetries. You have some.
Yeah.
If you impose some boundary condition, then that would require some non-local constraint on the initial data on the spatial part, right? I mean, if you put some condition on the radiation, on the time-like component, then it means that you cannot put arbitrary local things in the space-like part of the boundary.
Sure.
So you're going to have this constraint somehow in this phase space.
Yeah, but this is always part of the. That's right. That's also.
But if you don't have gauge,
local fields will not be your phase space variables. That's what I mean. Do you see what I mean?
Not quite.
In the global Cauchy surface approach, then values of, let's say, a scalar field without gauge transformations, then the value of the field and its time derivative, it's your phase space variables at each point on the surface.
But that's because you have imposed asymptotic boundary conditions. So
yeah,
so
or if you don't have boundary conditions, say compact states. Now, if you put time-like boundaries, then what happens on the boundary depends on what happens on the space-like part. Because of radiation, right? I mean,
well, not if you impose only boundary conditions on half of the degrees of freedom, right? Like if you just fix
I mean,
the
it's
usual
just
boundary conditions.
no, but I mean, sorry. When you fix the boundary conditions, so you're gonna say whether there are waves coming in or waves coming out, and that is immediately going to give you some constraints on the initial and final slices. I mean, that's whatever boundary.
No. If you don't have gauge symmetries, there is no constraint on the initial
just a
slice.
scalar field. Forget about constraints. Just take a scalar field.
Yes.
Now the scalar field may have, let's say, massless, so it has wave solutions. Now you fix the boundary condition on the time-like cylinder at the finite distance. That is going to give you automatically a restriction of the phase space, which a priori don't know exactly which one it is, because it depends on the details of what you fix.
No, that's not true, I think.
What do you mean it's not true? Boundary condition is going to tell you whether there are waves coming in or out. And of course, that is
but you still have in the bulk the value of the fields and the normal derivative to the Cauchy slice are still.
And you agree that if you change these, you're going to change the flux of wave-like solutions that go through the time-like boundary.
Come on, you just can you let me finish my sentence before jumping? Well, I don't know what I was saying. What did you say?
So maybe it helps to think about it this way, that we're looking at the full space of solutions, the global space of solutions, and we're just post-selecting from the full set of solutions those that satisfy.
That's right.
Certain.
Exactly.
But
so it is going to be some subset. Yes.
Yeah, of course. But that's exactly what we want, and that's
that's fine. In fact, I personally had no problem with that. And Alejandro was just asking, do you agree that there is going to be some restriction? And you agree.
Of course, but that's the whole point. But that's the whole point.
But it's not going to be. It's not. So it's just to understand, okay? So the parameterization will not be based on the value of phi and its time derivative at each point on sigma anymore. It would be a complicated, non-local parameterization of the phase.
It will still be in this way because we are not imposing too strong boundary conditions. We are just imposing boundary conditions on like, let's say, Neumann or Dirichlet or something like this. So you still have in the bulk the degrees of freedom per points are still the same.
But you cannot span that's right. That doesn't change a priori, but unless you're too restrictive. But you're not spanning the full space of solution that you will be spanning with a full Cauchy slice. Philippe seemed to agree.
Yes. That of course, but that's necessary if you want to obtain a phase space in the end.
Yeah.
Right. But if you
that's the whole point.
It's not necessary. If you take a boundary,
it's the whole point for the
follow-up conditions, you span the whole phase space.
Come on, I mean, it's the whole point for getting the phase space of the subregion subject to certain boundary conditions.
Yeah.
So that's why we also call it post-selection, because it's post-selecting a subset of solutions from the global space.
Sure, that's fine. And my question concerning this was, in order to characterize what the subset is, let's not do it in practice because in practice it's going to be complicated. But even in principle, you will also need to fix the part of the boundary condition which concerns the gauge. Otherwise, you will have many representatives of the same physical trajectory. So my question was about what is the point of doing the split of just fixing the radiative boundary condition and the gauge boundary condition? Because from the point of view of constructing this reduced phase space, we agreed it's a reduced phase space. Shouldn't you need both or not?
Yeah, but except that, yes, so in order to obtain the reduced phase space, then you have two choices. You can either look at the space of orbits or you can gauge fix. But that's the same as in the global picture. So,
right, so if my question is, what is the relevance of the intermediate construction in which you only fix the blue equation and not
So
the
I think what we were trying to do is exactly to disentangle the two steps. So what is the type of physical boundary conditions you are imposing, and in which sense they lead you to edge modes? And that step we want to separate it from the further step that you need to take in order to obtain a phase space in a gauge theory, which usually is quite involved to take the symplectic reduction. So
Thank you.
yeah. Yeah, okay. And just to take an example in Maxwell, where, well, just the frame field is just a U1 field here. So when you dress the connection, you get a non-trivial dressing. So A minus d phi here, because A is not gauge invariant by itself. But of course, if you dress the flux, the field strength, this has no effect. And as a result, this omega rad here that I denoted here in Maxwell is just this object here. And so the two natural boundary conditions you may have are, well, first, the Neumann boundary condition. Sorry, I have someone ringing my bell, but the Neumann boundary condition is does not require any dressing, because it's about fixing a gauge invariant observable that is already gauge invariant by itself, while this relational type of Dirichlet boundary condition is gauge invariant, but it refers to not to A itself, because fixing A, as I was trying to say earlier, is not fixing a physical observable, it's fixing a physical observable plus a specific gauge fixing condition. But the combination of A minus d phi, where phi is the frame, of course, because it's gauge invariant, it allows you to go through the construction. And also I think yeah, and this type of boundary conditions will lead us to edge modes, while the first one not. You should construct the regional presymplectic structure for the Neumann boundary condition. The edge modes will drop out from the construction, while with this relational boundary condition they won't. So I think what this is saying is that these edge modes, they are really relevant when you start implementing boundary conditions that are intrinsically relational, that relate what's going on in the region M to some external dynamical reference frame. So I think that's part of the reason why we want to do this construction, is to get this type of insights, that the edge modes, they are not really, I don't think they have a meaning on their own as local fields, but they capture, in fact, relational boundary conditions, and they are necessary if you want to impose this type of relational boundary conditions. All right. So I think I need to speed up quite significantly. So yeah, okay. So once we have this, we are in this setup, we can then try to throw away as much information as we want about the complementary region M bar. And because we have boundary conditions now that do involve the frame in general, we need to retain some information about the frame field, but we can throw away the information about A bar. So we keep as dynamical variables the connection in the region M and the frame field on gamma. And that gives you the extended phase space a la Laurent and Will, except that we got it by restriction in a way, by post-selection from the global picture. So it's a kind of reverse process. And I guess both constructions inform each other. And from there, one can then derive what should be the the appropriate presymplectic structure on this space of solutions in order to turn it into a covariant phase space by making two natural postulates. One is that one should want in this global picture that the presymplectic forms are additive with respect to gluing of subregions. So the presymplectic structure of region M plus the presymplectic structure of region M bar should give you the full presymplectic structure. And so that leads to an ansatz where, well, omega M should be the naive term, which is just the integration of omega on sigma, plus possibly a boundary piece, provided that you also subtract the same boundary piece from the complementary region presymplectic structure. And so, and from that ansatz, so that's the first point. And the second point is that because now we are looking at a dynamical situation here where we can look at different global Cauchy slices, what we may ask is that omega M should be conserved, so independent of the trace of Cauchy slice. And that leads to a condition that on shell of the boundary conditions, you should have the gauge part now of the presymplectic structure be related to this boundary piece in this way. And so that almost uniquely fixes omega partial, the boundary piece. And if you apply that to standard examples, for example, Maxwell, you do recover, in fact, the same presymplectic structure as Donnelly and Fredel, but in a slightly different way. So we never had to say anything about field-dependent gauge transformations, for example. Okay, and now I will just skip this. So we can, in fact, lift this whole construction to an off-shell construction and obtain, well, boundary actions, including boundary terms that, in fact, implement the boundary conditions dynamically. But I will skip this. So in the paper, there is a kind of general algorithm that can be implemented into any theory. And because of the time, I will move on to. I will also skip this section and move on to gravity. So in this section, the main point I wanted to stress is that, say it quickly, is that in the presence of gauge symmetries, in fact, we need the boundary symmetries need to be separated into several further subclasses, 3 of them. So the first one is our physical symmetries that in fact leave the boundary conditions invariant and also remain non-trivial in this space of solutions with boundary conditions. You can also have the situation where these boundary symmetries they become entirely gauge, so they become null directions even though they leave the boundary conditions invariant. And then you have the third situation where they don't even leave the boundary conditions invariant. So in this language, they map one regional phase space to another one specified by different boundary conditions. And this interplay between boundary conditions and symmetries can be very different depending on the leads to very different situations depending on the theory you are interested in. And for example, in the paper, we contrast Yang-Mills theories where this type of these physical symmetries, physical directions that you end up with at the end of the day in the let's say the physical phase space are always finitely many, while in Chern-Simons, in abelian Chern-Simons, they remain infinite. There's always a functional worth of such direction. So the edge modes dramatically increases the dimension of the phase space, while in Yang-Mills they don't. Even though
I'm curious about this.
Because boundary conditions, it looks like adding the edge modes is greatly extending the phase space.
Can I ask a quick question?
Okay, and now let me move on to gravity.
Sylvain?
Quickly, do you have 5 minutes?
Yeah, I don't know if you hear Simone was trying to ask.
Or it's too much to ask.
Yes, Sylvain, can you hear us? I think Sylvain cannot hear us anymore. Sylvain?
Yes.
Can you hear me?
Yes.
Ah, okay. Yes, I think Simone had a question.
Ah, okay.
And yes, you have yeah. You
Yeah,
can,
no, don't worry. You're running out of time. I'm sorry.
yeah, we can, if you
No,
want,
it's
keep the
fine.
question for the end, and if
Okay.
Sylvain, if you want.
Okay, so let me try to give you a sense of so the main claim about this last part that I wanted to mention is the fact that, well, the first paper we wrote with Philippe is about gauge theory solely, but now in work in progress with Stefan also, we are applying it to gravity, and it works very nicely there as well. So it's still work in progress, but the upshot is that it's applicable, and we also recover the gravitational edge modes that have been derived by other methods in this framework. So of course, a key difference in this gravity context is that the dynamical reference frame that I was mentioning here is already required to, in fact, provide an invariant definition of the region itself, because the spacetime is not background. So to specify the region M, you already need some kind of reference frame. And so one cartoon example I can give here is suppose that you are looking at a local region in field space where you have a set of spacetime events that allow you to localize points in your spacetime by, for example, looking at the geodesic distance from a point X to these events that you have defined by coincidences, so they are really physical quantity. If you have that, you can construct this object here, U, which is a map from the spacetime M union M bar to some parameter space. Okay, so these parameters here are the distances from your point of interest to these events, and you can show that it transforms in a nice way under the diffeomorphisms of spacetime, and particularly transforms like this, just by the natural action. So this is the analog of the kind of the group valued reference frames that we had in gauge theory. So it's a map from spacetime to a parameter space that transforms like this. It's an embedding map, another way to say it. And so this type of construction has been used recently, in fact, by these two papers. But well, I'm using my own. I'm using our notations, which are slightly different, but otherwise it's the same idea. So at the end of the day, this U, you can view it as an embedding map from spacetime to this parameter space. And that allows you to define the region M, the boundary gamma, or even the Cauchy slices as in an invariant way by defining them as the pre-image of some region in this parameter space. And this parameter space is really the physical, the space of physical observables. They are like the invariant distances from such and such points to such and such events. And so because of that, given a covariant Lagrangian on spacetime, the action for the subregion M is already defined in terms of the frame field. So you are integrating over the region M, which is defined as the pre-image of subregion of the parameter space. And so as a result, written on the parameter space itself, the Lagrangian, in fact, is really the push forward of the spacetime Lagrangians by the frame. So it already contains the frame. And so that's one key difference with gauge theory, because then the relevant covariant phase space formula is not the one about that we will start from. Is not really the one about the spacetime Lagrangian here, but it's the one relating to the dressed Lagrangian U star L. And if you compute the the symplectic potential associated to this Lagrangian is not just the naive one, theta. It's decorated already by the frame field via this object that is called delta chi, which I now introduce. So this, okay, this is a bit much, but sorry. This presymplectic structure already involves the frame through this object, which is a kind of Maurer-Cartan form. I don't have time to detail too much. So it's expressed in terms of this embedding field U, which is dynamical, and it's a one form that takes value in the vector fields on spacetime, and it's not in general exact. Hence this notation, and the reason why the symplectic potential is not just theta, but this theta of chi is because the push forward by U and delta, they do not commute because U is field dependent. Instead, you have a relation of this type where now you need to use a covariant derivative, delta sub chi, which is defined in some way with respect to this Maurer-Cartan form. And the key point is that this field space covariant derivative is flat. So for example, you have that it squares to 0. Okay, and so just all in all, the basic presymplectic structure we start from in this type of setup is already addressed. It's this U star of theta chi, which is expressed like this, and the presymplectic current can be computed as well. And again, it's already addressed, so it's given by on shell by this omega, and there is also a boundary piece already before dressing, in fact. Before the frame construction I had already introduced in the gauge theory case, there is already a boundary piece that contains some frame information. And then from there we can apply the algorithm that we have developed for gauge theory to this context. That is, we can decompose this bare symplectic structure into an invariant piece and a gauge piece. So I will not tell you exactly how it works, but it works basically in the same way as in gauge theory. And one obtains this type of formula. So the invariant piece of the symplectic potential is this theta decorated with the frame in this way. It doesn't matter what it is. More interestingly, the gauge part of the symplectic potential is related to this to the natural current of the theory, evaluated on this variational vector field here. And because of that, thanks to this observation here, we can show that the construction we have developed for gauge theory applies directly. And this is due to the fact that, well, in gravitational theories, the natural current is trivial, and there's, for example, a nice historical perspective on this in this paper, in the sense that it's a sum of a constraint and an exact term, which involves this charge aspect Q of psi. And this immediately implies that this theta gauge here that I have written here is exact on shell. And is expressed in terms of this charge aspect in such a way. So for GR, you have a formula of this type. And because of that, so this is the basic consistency condition we need to have in order for the algorithm to go through. We need that the gauge part of the symplectic structure is exact, and then this what's inside this exact piece is going to be the boundary presymplectic structure we need to add in order to make the presymplectic structure conserved. And so going through this construction, we get for presymplectic structure for the subregion M, the bulk piece, which is just the bare presymplectic structure I told you about before, which already contains the frame, plus another boundary piece that is also that depends on this Komar charge object here. Okay, and then once we have this presymplectic structure, we can study these two types of symmetries, transformations that have been studied by, well, for example, Donnet and Fredel. So they are the diffeomorphisms on M and the diffeomorphisms on the parameter space, which will be the symmetries. So, and the upshot is that all the diffeomorphisms on M, they remain gauge directions with respect to this symplectic structure, as we would hope from this point of view of our general construction. And so, more specifically, if you compute the diffeomorphism charge related to this psi here, you get constraints, so that vanishes on shell, and so they are gauge direction, and this does not depend on how psi behaves on the boundary. Okay. And then more interesting, the diffeomorphisms acting on the space of observables, of invariant observables, that I have denoted by rho, they give an interesting structure. And so if you compute the charges, the contraction of the field space, vector field associated to these diffeomorphisms, so they act non-trivially on the frame here, delta chi, but they don't act on the space-time fields like the metric. You get two pieces as usual in this context: a charge here, which is a field space exact, and a flux. The charge involves again this Komar term, and the field space, the flux is of this form. So it's a kind of dressed version of formulas that already exist in the literature. And as is standard, then you can study under which conditions these directions, these vector fields, they become integrable. And so there are at least two ways one can do that. First strategy is to just looking at the flux, the form of the flux here, you can restrict the vector fields rho to leave the Cauchy slice invariant. So the Cauchy slice in parameter space, not in space-time. And so we haven't finished this computation, but I presume that if we go through it, we will recover the universal corner symmetry of Donnet, Fredel, and others. But I need to check that. And the second option, which is more in line with what we were doing in the gauge theory context, is to impose boundary conditions on this boundary gamma that make the flux vanish, or at least become exact. And the kind of general boundary condition we can impose is of this form, in fact. So again, I don't have time to tell you more, but it can be expressed in terms of a boundary Lagrangian L in a similar way as in this work by Halo and Wu, but now in the kind of dressed version. And if you do so, if you do impose this type of boundary conditions, you get integrable charges, but the charges are, so the flux is not necessarily vanishing. It brings an additional term to the charge, which depends on this boundary Lagrangian. And this charge, they obey a nice conservation law, for example, in this form. So if you compute the charge on sigma 2 and on sigma 1 and compare them, you get the difference contains the flux term, which depends on the anomaly of this boundary Lagrangian U star L. So you will get a flux whenever this boundary Lagrangian fails to be covariant under frame reorientations. So, and again, this is a kind of frame dressed version of formulas that have appeared before, for example, in these works. And yeah, I guess I will stop now. That's it. So well, here's the kind of summary. I hope I convinced you that this frame understanding, reference frame understanding of edge modes, like brings maybe some of the physical interpretations of this formalism to the forefront, and yeah, illuminates certain aspects. I hope. And it's quite general, so we have applied it by now to Young Mills, transassignments, and also gravity. And okay, now what remains to be done is to understand, well, statistical aspects and quantum aspects, and see whether this quantum reference frame, this reference frame understanding is going to be useful in this, for example, in this general framework of local holography, or yeah. This remains to be seen. Okay, and thank you, and sorry for being over time. Yeah.
Right, thanks a lot, Sylvain. No worries about the time. In fact, we still have time for questions now. So please go ahead. Yes, Daniele.
Yeah, hi, Sylvain. Thanks for the nice talk. Just a clarification. In the gravitational part, in the last part of the talk, the diffeomorphisms you're talking about are also field-dependent diffeomorphism, so dependent on the metric as well, or not?
No, they were not here. I was assuming. I think so. We haven't done so, but I'm pretty sure we can extend this, I mean, generalize these formulas to field-dependent diffeos, but we haven't done so yet.
Okay.
So here I was assuming that they are field-independent, and it's a bit the general philosophy that we are following also in the gauge theory context, because these field-dependent, independent transformations, they are really frame reorientations, while the field dependent ones, they don't have this nice interpretation, so they are more.
Okay. Yeah. Thanks.
Yes.
More questions?
Can I ask a question?
Yeah, sure, please.
I'm not sure if there was Simone before asking a question, so maybe as priority during the talk. I mean, otherwise I will ask.
Yes.
So my question is about the boundary Lagrangian in the gravity in the gravity case.
Yes.
I mean, for the gauge theory part, you said quickly that you can go off shell and recover the boundary Lagrangian for the Maxwell case, for instance.
Yes. So
selection. Have you also tried something similar for the gravity case?
Not yet. We just started looking at that, but it seems that is going to work in the same way. But well, it has to be seen. So yeah, the main idea is that in order to get to the boundary action, what you want to do is lift this type of construction I told you about from the on-shell level to the off-shell level. And okay, there are some ambiguities that occur when you do so, but more or less you get to natural prescription for the boundary Lagrangian that allows you to implement the boundary conditions dynamically. Yeah, but yeah, we have to see. Yeah, Stefan started to look at this, but yeah, I don't know. Maybe he has more insights, but I don't see it. Yeah.
Okay, well, up to the test, you expect the construction to work still.
Okay.
More questions? Maybe in the meantime, I ask one. Yeah, I was wondering if you have thought about the possibility or the need to introduce another layer of edge modes in the gravitational case, because as you explained, in gravity, in a sense, you already kind of from the onset have this frame U, which is here.
Yeah.
So does it mean that this U plays exactly the same role as the frame you had before, or it means that you still need somehow to introduce an extra set of frames? And one extra motivation would be to, maybe this would be a way to understand this, the flux term, which here you have to deal with boundary conditions or choosing the vector field. But is it plausible that by introducing extra edge modes, you could also kind of do something with this flux term?
Well, good insight, but well, I don't know. Did you?
In fact, somehow I thought that this is what Laurent had done in his recent paper alone, that he had kind of modified his prescription.
No. Okay. So, but that I know. So, so in fact, what Laurent and others have done, like Chamberlain, is to use as a symplectic structure simply this omega k. So you integrate this omega k over the partial Cauchy slice sigma, and then they find that all the diffeos, what was the statement? All the diffeos become integrable and have non-trivial charges, so you don't have a flux. But there are aspects of this proposal that I don't quite get because these diffeos from the global perspective, they are gauge directions. So all of a sudden, because you have chosen a symplectic structure that make them not gauge, you are turning, these diffeos that are gauge symmetries into non-trivial transformations. So this is a bit weird. Yeah. And also, if you compute the charges of the symmetries with respect to this symplectic structure, you also get something that is not making a lot of sense. So I mean, to me, like it seems that the symplectic structure that we have, which I think should be up to some extra conditions, maybe that they took, I don't know, should be more or less the same as the one by Laurent and Will. I'm not sure. I have to check. But this one where you also include, what I was saying is that the symplectic structure they looked at is simply the first term here. It already contains a boundary piece, but not the one that is contained in this guide here. But if you don't have this one, then you don't. The diffeos are not anymore gauged, and the symmetries, they don't have the nice structure I told you about. They are So I don't know what that means. And also, like the way we arrive at this symplectic structure, I mean, if you don't include this term, then the symplectic structure is not conserved even when you impose boundary conditions. Yes. So even if you don't impose boundary conditions, I would say that you want that the symplectic structure is conserved once you do, because that's the whole point of boundary conditions, not that you because you have boundary conditions, you can make the system, consider the system as a kind of closed system. So it seems that, well, my current understanding is that this is a better structure than just keeping the first term. But
okay, so okay, I had missed that you had so the second term you have here is not used by Laurent.
No, it's just so what we are doing is really using what Laurent and Chamberlain did as the basic presymplectic structure that we then dress further by following the algorithm that we have developed in gauge theory.
So you have a second dressing in a sense.
Yeah, but it's by the same the same field. So for example, coming back to your question, what I was wondering is whether introducing further dressing might be useful to get the other types of symmetries that you have developed. For example, you have computed, like the ones you get from first order gravity, for example. So I was wondering if instead of viewing these extra layers of symmetry algebras as coming from a different formulation of gravity. Maybe they can come already from just a addition of another frame, for example, a frame field that you could shoot from infinity as well. And then maybe this gives an alternative derivation of this type of structures without still in metric gravity, but you would still get this frame. But we haven't looked at that.
Yeah, that would be interesting.
Yeah.
Okay, thanks.
Yeah, you're welcome.
And more questions?
Can I ask a question?
Yeah, please. First.
So I got disconnected towards the end, so maybe you said something about this and I missed it, but can you see from your formalism the dependence of charges of your symplectic structure on boundary conditions? On a type of boundary condition?
Yes.
I mean, when you choose the type of
so you mean in gravity now, or?
I mean in gravity. Yeah.
So in gravity, we haven't looked at it yet, but that's the next step. So, but in gauge theory, yes, we in fact investigated various types of boundary conditions. Dirichlet, Neumann, or Robin, and looked at how this what was the interplay with the symmetries. And in fact, for example, in Young's, if I remember well, the symmetries they essentially drop out unless you use very specific types of boundary conditions. Like Robin, if I remember correctly. So you can see this interplay, but I had to skip this part because I was rushing through this section. But yeah, it was it was here that I was trying to emphasize this point that once you impose boundary conditions, then there is a further split of these symmetries into different types, and they can become gauge, they can remain symmetries, or they can also map you from one set of boundary conditions to another. So this is what we call meta symmetries, because they map from one phase space to another. And yeah, I'm not sure if this is answering the question.
Yeah, okay, thank you.
Okay, you're welcome.
All right, one final question maybe. Okay, if not, we can thank Sylvain again. So thanks.
Thanks. Thank you.